Welcome to the Bug Bash podcast, where we talk about all things software correctness and reliability. I'm your host, David Wynn. Large language models can generate code in a flash, but that code is notoriously unreliable. Traditional unit tests often can't put in enough guardrails to ensure correctness, even if they're written by the LLM itself, or maybe especially so. This is where property-based testing becomes essential. Today, we're joined by David MacIver, creator of the property-based testing library Hypothesis. We discuss how to build robust feedback loops that are needed to make AI-generated code trustworthy. We'll cover why standard AI coding benchmarks are flawed, how Hypothesis makes property-based testing approachable, and the challenge of getting developers to think in invariants. David also shares his perspective on the future of AI in software engineering. If you want to build a reliability backstop for your code, vibed or otherwise, stick around.
Hey everybody, welcome to another episode of the Bug Bash podcast. We have a very, very exciting and special guest with us today. His name is David MacIver, and you have almost certainly used his stuff if you have done anything related to property-based testing. David is the creator of Hypothesis, the most widely used library for PBT. He has also done a lot of cool AI stuff at Anthropic, and he also knows a lot about test case minimization. We're going to try and cover all those topics and others. Welcome, David.
Thanks very much, Will. I should say it's actually David MacIver, not MacIver.
I'm so sorry.
It's okay. We're here to catch bugs, and it's very kind to say I've done lots of cool stuff at Anthropic. I did some cool stuff at Anthropic.
And you probably cannot tell us what it is.
I can tell you that I worked on LLM evaluations, among other things, and I can tell you more interesting things I've done with LLMs after Anthropic, but that's where my interest in how they were evaluated got started.
So speaking of LLM evaluations, I have recently done a little bit of a deep dive into coding evals in particular that have been used with LLMs. And we can talk later about why that was. But I was a little bit horrified to discover that
they're all terrible.
They're terrible. They're so bad.
Yeah, it's
and even the benchmark, SWE-bench verified, which has verified right there in the title. It's like we, you made some change and did the unit test pass. And I feel like the people on this podcast are well aware that just because the unit test pass does not mean that the software is in any way correct. And I recently read another paper which suggested actually a very large number of passing examples in these benchmarks do not actually work in any way. What do you think?
So that's certainly what I haven't looked super in depth in the quality of the sort of the standard coding benchmarks in the last couple of years. When I last looked at this, it was certainly the case that your standard coding benchmarks like human eval, they would regularly, in some of the cases, their gold standard example from the evaluation was also wrong, but they would regularly accept things where if you just added a couple more test cases, you would see that they were wrong. There was a paper that came out a couple of years ago about human eval plus, which was essentially just doing the bare minimum to add a bunch more verification to the human eval is also called codex often. I think it goes by a bunch of different names. I can't remember why it goes by all these different names, but it was for quite some time your sort of gold standard coding benchmark. And when you just improve the quality of the testing in it, all of the LLMs get a meaningfully worse result because they were quite regularly just giving things that failed, often not in even interesting ways. Often your standard property-based testing, if I pass an empty list here, it fails, or this fails if that number is 0. But I think there were also more interesting failures as well, but I don't remember any of them.
I suppose it shouldn't surprise us that in interviewing our models, we recreated the same ridiculous process we used to interview humans.
I have used property-based testing in interviewing humans before, and it does work very well.
To
have a full property-based testing suite for evaluating coding tests.
I assume that if this is true of the benchmarks and the evals, it's probably like I know you cannot comment on this, but I assume it's also true of the reinforcement learning process that's used to post-train these models for coding as well.
Thankfully, I don't know anything about that. So which means I am allowed to comment on it. I would imagine that at this point, people are probably doing better evaluations and post-training internally than the public benchmarks suggest. I have no insider knowledge to say about that one way or the other. So I'm speculating wildly, but we've seen some really quite impressive improvements in maths and coding in like the last year or so, and I cannot imagine that we got those without them having some degree of better internal benchmarks that appear in the reinforcement learning, but I don't know what those are.
Yeah, interesting. A thing that I have noticed is that coding agents tend to do very well at tasks that are like very local, in the sense that like all of the code fits on a screen, or that the kinds of bugs that can be introduced are the bugs that you can notice by looking at like a screen. And they tend to be quite bad at changes or at avoiding problems that involve the interaction of a bunch of disparate pieces of code. And my initial guess as to this, and I think the conventional wisdom in the industry still, is that it's because of the context window. But I feel like as context windows have expanded and we've gotten better at stuffing more and more stuff into them, this has like not drastically improved. And so now I'm starting to suspect that it's actually because the kinds of tests that are being used to give these things RL feedback are maybe not great at catching issues that connect multiple disparate parts of a software system.
Yeah. So my understanding of the RL loop isn't great, but I think most training still happens on small context windows would be my guess, because it's or if not small context windows, like with things that would fit in a small context window, because I think it's so much more expensive to do good reinforcement learning on something that is like 100K or what 1 million or whatever the current context window maximums are. I don't actually know. So it's possible that some of that's context windows. But yeah, I think probably it's more in the training data would be my guess. But again, this is not something I have insider knowledge of. I'm just speculating. But it does seem like it's both sort of like easy to sort of see why it would be easier to train models for one-shot tasks and than like complicated interactions of things, because there's just like it's much easier sort of straightforward reinforcement learning setup, right? Like here are your examples, do a thing, did you get it right? I actually haven't spent a huge amount of time with the proper coding agents, and is the funny thing. Like I use AI a fair bit in coding, but it tends to be sort of go to Claude or ChatGPT and say, hey, can you write me a thing? And then I copy and paste the thing it wrote me into an editor, and then I inevitably do a bunch of work to make it actually work. And it's still often super useful for like doing things that either I don't particularly want to do or in an unfamiliar area. Like I've definitely vibe coded web UIs, which I'm terrible at writing myself, and they sometimes even worked without me having to do a bunch of fixing.
Have you had success getting these agents to write property-based tests for you? Like not the libraries, but the tests.
I've had medium success. I think it's not something I've tried to do very recently, actually, because, I as I said, I tend to use these agents in circumstances where I don't know how to do the thing. And so it's not necessarily and so like I've got some idea of how to write property-based tests after all, so I don't tend to reach for them naturally when doing that. When I've experimented with this in the past, what I found was with Hypothesis in particular, they were pretty good at generating the right data, and the tests they wrote were sort of boring and or slightly bad, but like not ridiculous. Like there's a common problem in property-based testing where people write property-based tests, which essentially like you recreate the application logic in the test and you assert that like the test version of the app and the application logic do the same thing. And that can be a super reasonable thing to do. Like if you've got a hyper-optimized real version and like a stupid, simple version that you can write in the test, and that's a perfectly reasonable test to write. But often they would do this where there wasn't like any really meaningful difference between the code they wrote in the real thing and the code they wrote in the test. But the generating data thing is interesting because that is, I think, one of the things that users struggle the most with Hypothesis. Like I've tried to make it so that writing a test using Hypothesis is just the same as writing a test not using Hypothesis. And that is sort of mostly successful. But the how do you generate good data is not something that necessarily comes super intuitively to people. And I think getting AI to do that part for them is probably like quite a good on-ramp to property-based testing. But
so that's really interesting because like you and Zach in maintaining Hypothesis have had this real focus on user experience and making it understandable and easy to hold for people, which has clearly led to this kind of steady growth in usage over time. Mm-hmm. And it's really cool that that API is factored well enough that LLMs can help onboard new users for you.
Yeah. Yeah, no, it's sort of, I think one of the interesting things we've been seeing over the last year or two is that LLMs are a real force multiplier on the thing that was good anyway, which is having documentation. Hypothesis has both like it doesn't have amazing documentation, but it has like a relatively comprehensible API, decent documentation. People write about it a lot. There are lots of examples on GitHub. And these are all of the things a human, and also on Stack Overflow, I think. These are all the things a human would use to try and understand it as well. But because they all went into the LLM training data, the LLM essentially like gets to distill a lot of that process a human would have used. I've heard an interesting argument that this is actually in some ways a bad thing because it creates a bit of a dampener on developing new tools because essentially it's like suppose someone invents Hypothesis++, like the next generation property-based testing, which is much easier to use than Hypothesis, then great. I would love them to do that. Hypothesis definitely shouldn't be the last word in property-based testing. But for quite some time, people will still prefer to use Hypothesis because the Hypothesis is the one the LLM can tell them how to use. And so unless Hypothesis++ is like easier to use than Hypothesis plus an LLM, then it will struggle to get traction.
So I think maybe we should take a step back here and talk a little bit about what property-based testing and Hypothesis are, and maybe why they might actually be about to go through a phase transition of importance in all of our lives. And I want to set you up for this with a sort of provocative statement. So I basically think that LLMs are extraordinarily powerful tools, and they're also extraordinarily unreliable. And the thing that allows you to turn something that's really powerful and unreliable into something really useful is being able to tell whether it's done the right thing. And, this is why generative models are so great for like image and video generation and for web UIs, because they're all things where you can kind of tell at a glance whether it did the right thing or not. And if it did, great, you accept it. And if it didn't, like you tell it to try again, and it tries again. And you can just do that in a loop until it does the thing you want. This is also why I'm actually pretty optimistic about using these things for like theoretical math, because we can actually mechanically check whether they have followed correct rules of inference. But I think that software, much as we might like it to be otherwise, is something where it can be really hard to tell at a glance whether something is correct. But I think possibly this other interest of yours, right, property-based testing and hypothesis in particular, like move the frontier on that. So feel free to reject anything I just said, or just give an intro of what you do. But that's how I was going to set you up.
Yeah. No, I think I agree with pretty much everything you just said. I'm maybe fractionally less optimistic about the current state of the art of LLM's ability to take feedback, but we can get into that at in a bit. So property-based testing, it's essentially testing where you get the computer to do some of the work for you, is the way I've often framed it. It's when you're writing a sort of a conventional test, you set up this very concrete scenario of like, here's some data, I do the thing with the data, here's what should have happened afterwards. Like that's a bit of a parody, but like that's roughly what a test looks like. With a property-based test, you instead say like, for all data that looks sort of like this, do the thing, and here's what should have happened. So rather than running on a single concrete example that you provided, you give the computer the ability to specify the range of data. And there's some sort of really easy examples of why this is valuable. One is like if you're doing some sort of like user login flow, you create a sort of a dummy user object, and you test your flow, and you probably called it, said like Joe Smith, joe@example.com, and so on. And that all worked. But like, what happens if Joe Smith is a mononym or has like a complicated Unicode character in his name or the like? What sort of email addresses do you actually accept? And just having the library provide the user object rather than having this one that you don't otherwise care about ends up testing a whole bunch of code paths that you might otherwise be neglecting. In sort of an early workshop I ran at a client, like someone commented that Hypothesis would be worth it if it was only for its Unicode strategy, and I think that's probably right. And you also can see this with dates and times, for example. Like writing correct date and time handling code is brutal, and the hypothesis date time strategy very carefully makes sure it covers all the nasty cases that you really wish it wasn't going to ask you about. I've forgotten many of the specifics, but the easiest examples of this are just like, have you got leap years right? Floating point numbers are another one, of course. Like the answer to is your floating point code correct is probably not, but you can sort of specify bounds in it. But then you can, but beyond that, there's like more complicated things. So you can use Hypothesis, for example, to generate sort of sequences of interactions. You can say like, I've got this API, generate random API calls to it, and see if some sequence of them breaks any sort of crucial invariants, that kind of thing. So it generally like opens up the ability to test a lot more than you manually would. And you're still having to sort of write the test yourself, you understand. It's not like a magic genie that says, find bugs in my code for me. For that, you want Antithesis, as I understand it. But it's sort of like, it's a force multiplier again. It's the amount of testing you do is probably like 10, 100, maybe if you're lucky, 1,000 times as much testing as you would if you were writing out every single example by hand. I mean, technically it's 100 times in that it writes 100 times as many examples, runs 100 times examples, but always per test by default. But the reality is that those 100 examples are probably not as good as 100 carefully handwritten examples, but they're certainly as good as 10 carefully handwritten examples.
I saw a study this morning, actually, which was an empirical investigation of Hypothesis. And they basically went and surveyed several hundred Python repos that used Hypothesis. And they found that on average, a hypothesis generator was able to detect 50 times as many bugs as a unit test in any of these projects, which is like pretty nice headline stat.
Yeah. So please send me a link afterwards. Because that is frankly better than I would have expected.
Yeah, they basically introduced artificial bugs using mutation testing and found which ones were found by what thing.
Fair enough.
But yeah, it's pretty sweet. So now give us your take on how property-based testing makes the AI adoption story easier, if you agree with me on that.
Yeah, so I think like this ties a bit into what we were saying about coding evaluations earlier, right? If you look at the human eval/codex evaluation, and simply adding property-based tests that assert that the LLM provided example is equal to provides the same answer as the gold standard or answer, which technically isn't a correct test for all of the human eval ones. There's like one or two in there where there's some ambiguity, but this ends up just catching like a huge pile of cases where the LLM produces a superficially correct answer that is wrong. So, in general, like you can't really trust AI generated code unless you've got some testing on it, and sometimes that testing is manually eyeballing it, like we talked about or you mentioned the video examples. We talked about the sort of the web UI examples, and they're like some of our manual testing is probably fine, but if you're getting the AI to write sort of non-trivial parts of your application, you want tests to check whether it actually worked. It usually didn't the first time, like and hot take, if you're going to write tests, they probably should be good tests. And property-based testing apparently catches 50 times as many bugs as normal testing. So I guess like that's the simple answer is that when you've got these AI agents that are rapidly churning out code and you want a source of reliability, like using the ways we already know how to improve reliability seems like a no-brainer.
In your mind, does that mean that the human operator must write the property-based tests to like clearly articulate their sense of the invariance? Because I was saying, like what I see in practice tends to be that most engineers who are letting an LLM write large portions of their application are even happier to let the LLM write large portions of their test suite. And so I have sort of a fundamental question about like what the tests are accomplishing at that.
I think that's okay. Like at the very least, it's a self-consistency check on the LLM output. Like the LLM has written the tests which indicate its beliefs about scare quotes, about what the code is supposed to be doing, and it's written the code and like actually running the tests does validate that it has at least a internally consistent mental model about what's going on. I think you're going to end up with a lot of problems like the one I was mentioning earlier, where it wrote the same code in the test and the application, so of course it worked. And so I think, so it's not by any means perfect, but I would say that it is at least better than nobody writing the tests. I think that the engineer should certainly read the tests and should sanity check them. I'm morally confident that most people aren't doing that, but I think most of the people who aren't doing that probably weren't going to write working code themselves either. So, and maybe that's too harsh. I don't know. But certainly, if they're not reading the test the AI wrote, then they probably weren't going to write the test themselves either. But
something I've noticed when trying to explain property-based testing to people is that there's a really big mindset shift from example-based testing to the idea of like invariants that should always hold true. And that a lot of developers have real trouble thinking about what the invariants of their code are. And I think this is not like a fundamental problem. I think this really is like a familiarity thing, because if you ask leading questions like, hey, should the answer always be a positive number? Hey, should the thing ever crash? Like people know what their invariants are. They just don't say what they are until they're prompted. So I'm curious, first of all, whether you have personally experienced this as like as a blocker to adoption of hypothesis, and then or if you have some clever way around it. And then I'm secondly, I guess, curious whether you think LLMs could help with that problem at all. For example, I don't know, maybe by reading your documentation and proposing some invariants for you.
So as far as invariants go, there's a sort of original sin of property-based testing, which is that it tries real hard to pretend that it's formal verification. I've forgotten the exact subtitle on the Quick Check paper, but basically Quick Check claims to be lightweight formal verification. It's not. It's a testing library.
Actually, the Amazon guys call their property-based testing lightweight formal methods.
That's right.
Yeah. And I think that thinking in terms of invariance is sort of a downstream of this original sin, which is like, yes, okay, obviously what a property-based test is it's asserting a universal property. It's saying this thing must always be true. But that's what most of your tests are claiming. They're not obviously actually universal. They're example based. They're a single thing, but it's still in some sense like if you look at a typical test name, the typical test name doesn't say in this particular example the thing should work. It says when non-empty user should be allowed to, or something like that. Like tests are already expressing invariants, and what I've generally encouraged people to do is to, rather than worry about what are the abstract universal properties of my program, start from existing example-based tests and try to generalize them. And essentially lean hard on the fact that people already know how to write tests, and go from those tests to properties rather than trying to learn an entirely new skill.
Yeah, that sounds really pragmatic. So is like concretely the way this works is like you have an example-based test, there's a constant 3 in it, and you try replacing the 3 with like, hypothesis dot give me a random integer. And then, if you notice there's also a 3 in the like thing we're checking, like maybe we need to factor that into a variable and use the same number in both places or something.
Mm-hmm.
Is that the
exactly that sort of thing? Or even more simply, sometimes you have constants and no, I guess not more simply. I was going to go back to the create a user object example, where you are creating user objects with constants that clearly don't matter, and getting a hypothesis to provide those. But yeah, but that is the same thing as your 3 example.
Yeah, I think Google may have actually pursued a very similar strategy recently. So they have this Google unit testing library called Test, I think, which is widely used inside of Google, and I believe also has been open sourced as part of ABSL. And I think they basically wrote a like fuzzing like harness that's called fuzz test, which is just like exactly the same interface as like your way of defining unit tests, except that you can like annotate a parameter with just like, hey, give me whatever you want here. And it just sort of all works exactly the same way. And I think they found that by doing that, they were able to hugely increase adoption of fuzzing within Google.
Yeah, no, that makes a lot of sense. And this is also why Hypothesis is just designed to run as part of your normal unit tests. Like Hypothesis is, well, historically it was designed to work with any testing framework. But yeah, having something where you don't have to pick up a new way of running your tests, you don't have to do anything fundamentally different from your existing approach. You can just sort of drop in a new library and start doing new things. Is, I think, super helpful for adoption.
I would assume that this Google library has some special support for generating a good range of protobuf defined data structs. And David, like, we've run into this interesting little Hypothesis extension that works with open API schemas to like generate fake data. Is that an approach that seems promising to you? Like, is this something that you guide people towards when you're doing these sort of training workshops?
This is a Hypothesis JSON schema or something else?
I believe that's it, yeah.
Yeah. Generally speaking, I think that it's worth writing your own generators if you can. It's one of the things I was relatively insistent on in Hypothesis with the typing support is that it's very easy to sort of gradually move away from it. So you can have like, if you've got a parameter to your test that has to be an integer, you can just say strategies.from type integer. I think these days there's even special syntax in the given decorator to do that. I don't remember what it is offhand though. But you need to make it so that it is easy for you to go, actually, I meant this to be a positive integer, and replace it with an explicit generator which says or strategy and Hypothesis, which is a terrible name. Hypothesis has a legacy of terrible names, and it's all my fault for not thinking about naming properly.
So we have those too. Early versions of the Antithesis API referred to, like, the literal ways of defining test properties, where you could call property.universal and property.existential to your point. And we thankfully changed those to always and sometimes.
Yeah. Yeah, it's definitely important to know when to change your names. Hypothesis, they got a bit too entrenched, and also in Hypothesis, we never come up with a better name for strategy, partly because the obviously correct name is generator, and that means something different in Python. And the Hypothesis name itself is just also problematic, but super entrenched. But anyway, to continue on the point, like being able to sort of gracefully bit by bit replace the bits that Hypothesis has done for you with bits where you have more manual control without having to essentially go all in on one approach or the other is, I think, super useful. And I very occasionally have found Hypothesis JSON schema super useful, but it lacks this graduality property where it's not easy to go from a Hypothesis JSON schema generated thing to something more constrained. I mean, you sort of can. Hypothesis has this filter method which lets you apply an arbitrary predicate, but it's not recommended as the main way to control your data generation because it essentially has to do rejection sampling. Try the thing repeatedly until you get a correct answer, which ends up with you throwing away an awful lot of data in some cases. So I guess, like, I don't want to be too negative about Hypothesis JSON schema. I think it's a great thing. I've often found and been very glad it exists, but it most of the time is not the thing I would reach for, particularly not when getting started with property-based testing.
I'd love to ask your take. We've touched sort of on UX a few times here, and I would love to hear your bigger picture thoughts about developing a good and approachable UX for a very complicated and difficult system, because I find myself facing the same challenge right now. And I think you're one of the most successful people ever at doing that, right? Like your colleague Zach actually gave a whole talk about this at Bug Bash last year. And I think it was really good and really useful for me, but I would love to hear your thoughts too.
I think that like how to do good UX is that there shouldn't be any cliffs. It's essentially like it's okay if your thing is difficult to use, but every time you have like a really sharp jump in the difficulty level, you lose people. And the first cliff that a lot of people have, or a lot of tools have, is on getting started. And so, and that's going to be where you lose like almost all of your potential users, right? And so with Hypothesis, the getting started story includes things like you absolutely can't have an external command runner that you have to use in order to use Hypothesis. It has to be integrated in your normal testing workflow. You need to be able to generate all the easy data you care about out of the box. You need to be able to those are probably the two big things. I guess like having a good setting system where you're like, if your tests take too long or if you're running into other problems, you can just configure the behavior is arguably a second one. So that's like the getting started story. And so anything that you can do that basically makes it trivial to get started is really like the most important possible UX thing. But after that, it needs to be like every time they want to do something new, then that needs to be easy too. Like you can imagine a world in which I figured out the magic prompt that gives an LLM the ability, like takes a project and produces a perfect set of hypothesis tests for it, right? That's, I think, not the world we live in right now, but like it could be the world we live in like 3 years' time, maybe less. But then the user has to maintain those hypothesis-based tests. And if it's not easy for them to gradually evolve the existing code base or to make change or to say, actually, this parameter now needs this, add this constraint to this parameter or make other changes to that, that's a new cliff. And it's not that they will go and delete those existing tests necessarily, but they're probably not going to like be enthused about keeping using Hypothesis. The other sort of big UX principle that I think drove Hypothesis early on was essentially just like pay attention to what's annoying. This really ended up being the principle that defined a lot of the Hypothesis API. Because Hypothesis has this internal shrinking thing going on where for those who don't know, shrinking in property-based testing basically means that when it first finds a example or a test case that makes your test fail, it's probably going to be big and complicated and hard to read. Shrinking is the process that sort of cuts out the unimportant bits and tries to turn it into a simple thing. And Hypothesis has a novel approach to shrinking that essentially means that you, the user, never need to even know this exists. With certain caveats of like you do need to know it exists when it does badly, but it usually doesn't. And classic property-based testing had two big problems with shrinking. One was that it would often break like the invariants you sort of carefully set up in your test data. You would say this has to be a positive integer, and it would always generate a positive integer initially, but shrinking would sometimes go, okay, it's currently 100, but what if we tried replacing 100 with -1? And so you would shrink from what was a real bug to a fake bug, basically, because your initial test case was a valid example demonstrating a real problem, and your shrunk test case was a something that just violated one of the preconditions, and so it doesn't matter.
Sorry, what? I'm not quite clear. Why would it sometimes do that? Presumably, if you know what the preconditions are, you could avoid violating them in your shrinking process.
So there are, if you've explicitly set this as a precondition in the test, as well as in your generator, then the shrinker would say, the precondition's been violated, so this is an invalid example. But if you just said, generate me an integer from 1 to 100, say, then that isn't a precondition in the test. It's an implicit precondition in the generated data.
I see. Interesting.
And in this example, it's easy to add a precondition. Sometimes it is like harder to impossible. Like the most dramatic example of this ever was when we. So I've successfully published like technically 2, but really 1 academic paper about hypothesis and about how its shrinker worked. And for that paper, we did a somewhat ridiculous flex of there is a code generator called CSmith, where which generates random C programs and has the guaranteed property that every program it generates is undefined behavior free. And then these are these large complicated programs that you also want to do shrinking on. And when you do this normally you use something called C-reduce, which cannot check whether the C program is undefined behavior free, because in general, this is just like I think in general, this is impossible. You can do a bunch of tooling that does conservative approximations. So you need to run it under Valgrind and like compilers with WL flags and so on and so forth. And so you can only do like a pretty good approximation to undefined behavior free checker. We just backed CSmith onto the hypothesis generator and got the hypothesis shrinker to run on it. And so it just like happily shrunk CSmith generated programs and got the undefined behavior free guarantee, well, for free because every shrunk program was a CSmith generated program. So it satisfied all of its natural guarantees.
Oh, okay. So your shrinker doesn't work by modifying the test input. It works by calling the generator again and asking for simpler examples.
Yep, exactly so. It manipulates effectively what it's doing is the generator is calling some pseudo-random number generator, and initially that is like something that looks like a normal pseudo-random number generator, and then during shrinking, it's something that hypothesis has like thoroughly rigged the dice and manipulates it in ways that causes the generated thing to be smaller.
Fascinating.
But and so
Interesting.
Yeah, so it never needs to touch the generated data, which is actually turns out to be a really important property in Python in a way that it wasn't in Haskell, because in Python you can mutate data.
Does your shrinker try to do ablation analysis as well? Like, will it just not invoke certain generators at all? Or like if you have a recursive set of generators, right? I have generator A, which can call B or C. During shrinking, will you just like deactivate C maybe or B?
No, generally not. From hypothesis's point of view, or from the shrinker's point of view, that's fairly opaque. Like when you've generated A, B, or C, all you know is at the shrinker level is that you requested an integer 0, 1, or 2. This then sort of picked the next generator, and then you requested some more bytes. It has a little bit more information than that, but not much.
Yeah, so it's interesting. So it might just be something to do with our domain and our customers. Like, I think when it comes to fault tolerance testing or distributed systems testing, ablation is very useful because root causing these bugs is often very, very hard. And so, being able to ask, is it possible to find the bug without fiddling with the clock? Is it possible to find the bug without restarting a process? Is it possible to find the bug without calling this API? Is like actually super helpful from a diagnosis and root cause point of view.
Yeah. No, I think this is a case where hypothesis and antithesis just have quite different trade-offs. I think hypothesis has a much sort of simpler class of structured examples than the sorts of things you're dealing with. I think that in it's the stateful testing, which is sort of what I was pointing at with the generating sort of long sequences of API calls, that is a case where some ablation might be helpful. We don't do any, but it might be helpful if we did. But I think for the most part, it doesn't matter very much if you're generating a relatively smallish structured test case for a specific test. The other big advantage hypothesis has here is just tests and hypothesis are super fast compared to antithesis. A slow test and hypothesis is you took a couple of seconds to run a test case, while I think in antithesis that would be a blazingly fast test case. So there are a lot of things that in theory could be helpful, but probably don't matter very much under these sorts of performance characteristics.
Yeah, I think that as with many companies, right, we have ambitions to world domination, but have started in one particular place. And I think that there's always ways in which the place where you start biases you and causes you to, view the world in an inaccurate way. And I think one thing is just, as you say, the systems we're testing are so big and so slow that the slowness of all of the rest of our system, it just doesn't really move the needle. And so we haven't been under very much pressure to make it blazing lightning fast. And I think that if we someday started trying to help the same users who today are using hypothesis to test their Python data structures or simple Python programs, this would immediately become a huge, huge, huge sticking point. And one good example of it is we don't really make much effort to make the first 5 seconds of the test the most valuable possible 5 seconds, and the next 5 seconds the next most valuable 5 seconds, and so on, right? If you're going to do a bunch of random stuff and generate a bunch of random cases, surely you should be scoring your random cases some way, or looking at whether they provoked bugs in the previous version of the software or something. You have some idea of how, where on the explore exploit trade-off this particular random case is. And you should clearly have a different bias towards different parts of that distribution over the course of your test, right? And that's just a thing that we've never even thought, we've never even started doing.
Yeah. So I think the obvious bit to start to me is something that hypothesis also did, which was is just having a test database. Hypothesis saves all previously seen failing test cases in both their original and shrunk forms, and uses those early on to just try those. And just having the original motivation for that was actually because hypothesis is right in your development loop. So if you have you run your unit tests and they fail, you want that when you rerun them, they fail in exactly the same way and as fast. But it's proved useful above and beyond that. And so it's not just that for retrying a single thing, it's also slippage occurred during test case reduction. So actually you started with one bug and you moved to another, and you fixed the bug you moved to, but not the original one, and things like that. So just stuff you have previously seen to be useful is just the lowest possible hanging fruit for early valuable things.
Yeah, Google's internal fuzzing as a service has, I think, a really pragmatic compromise on this. Basically, if you check in code into Google, which has a fuzzing target defined, it will just get fuzzed continuously with spare Borg cycles. But if the fuzzing finds any crashing inputs, those get added to a seed corpus for your particular piece of software. And those then, it just runs through every such crasher pre-commit on every future, every future time you try and commit code, which I think is a nice way of balancing the pros and cons of exploration versus running things will crash.
And they have effectively open sourced that. That is exactly how the Go fuzzing support works. Yeah, I always found like as a user, the user experience of this in Hypothesis is really nice because it just kind of completely eliminates the need for you to write regression tests. Like I found a bug because I was writing bad code in the way that I will probably write bad code again in the future. And I don't need to specially like take a moment to reify my idiocy in a handwritten example test just for free. And often like slightly quietly, so I don't need to point everyone else at it very explicitly, get this nice database entry that protects me from that class of bugs later on.
I do often end up adding them as explicit examples in the source code when I run into like a bug that makes me go, oh yeah, that's a good point. I should probably check for that. So Hypothesis does also let you, as lightweightly as possible, add them as a regression test built into the existing test as part of your source code.
That's a great
That
feature.
is really nice.
Yeah.
Yeah. It's basically you add an @example decorator or in the test. It's these days, I think it will usually even suggest, like, offer to or it creates a Git patch for you and says, "Would you like to apply this patch?" It's
whoa.
I keep running into bugs with the Git patch feature that I haven't been able to track down, ironically. So like I find that like the automatic patching only works about 50% of the time for me, and I keep meaning to sort of take a weekend and sort of dig into why that is. But it's a great feature when it works, and and it's not hard to do it by hand, even when you don't get the automatic patch apply.
This is strikingly similar to your view on LLMs and reducers in general. Like it only works 50% of the time, but you can tell when it's not working. So 50% is still useful.
Yeah. Yeah, no, absolutely. Although this particular one I would like to work 100% of the time.
Right.
And I feel this is more achievable than LLMs.
That's fair. It is a more tractable problem.
Yeah, I feel like our spin on the like it's okay if it works a small percent of the time is if you have a time machine, then a tactic that works 1% of the time, 5% of the time, I mean, it's incredibly valuable, right? Like you just rewind and then you keep doing it until it works. And that's sort of, I feel like that's a very useful intuition pump for why techniques like fuzzing or like antithesis can do a better job of testing software than like a very, very smart RL agent, without being anywhere near as smart or as good at RL, right? It's like an RL agent needs to have a policy that works 99.99999% of the time because, it needs to succeed a single run through the program.
I think there's something to be slightly careful of in all this talk about like what percentage of the time something works, which I think is sort of pointed at a little bit by your time traveling example, which like there's a really big difference between in 100% of cases it works 90% of the time and in 90% of the cases it works 100% of the time, right?
Yes.
Like it's very easy to write software. So, and I think LLMs are often an example of this. Like an LLM. So you'll see in a lot of the LLM evaluations these pass at K metrics, which is essentially if you give it K times to try, does it succeed? Like how often does it succeed at least once in those? So like pass at 5, for example, means if it tried 5 times, were any of them a success? And so what you will see is, say, an LLM has a rating of 80% on some benchmark in pass at 1, and if it was truly like independently 80% successful, then you would expect that like pass at 2 is, oh god, I can't do the mental arithmetic in my head, but it's going to be like 90%. Like the pass at K would converge to 100%. But in reality, what happens is like the pass at K converges to 85%. These are all made up numbers, by the way. I'm not like citing a particular benchmark. As all of the unreliability is in the example rather than in the LLM's response to the example. Well, not all the unreliability, but like there's sort of like two different metrics. One is the fraction of test cases in which it's plausible that it works, and the other is the like reliability of it working on test cases that it works. And those lead to two different numbers, which you do need to make importantly different trade-offs around.
Yes. We have an interesting version of this problem, which is, Antithesis has many tactics that it can use to try to make your system do something cool. And perhaps, let's imagine one of those tactics was completely ineffective, right? It never did anything good. Well, we're like, aha, we're very clever. We've bounded the amount of energy that our fuzzer can spend using any given tactic to some fixed constant of the total exploration energy. So if say I give each of my tactics 1/n time in the fuzzer, then like at worst, they'll make me like that % less efficient. And so I've got bounded downside if I just add a random new tactic. But it's actually not quite right, because a tactic they can sort of destructively interfere, right? A tactic could continuously drive the system under test into a state where it's really unfruitful to do anything, including with any of my other perfectly good tactics.
Mm-hmm.
And so actually this math doesn't quite work out unless you go to a lot more trouble, because there's all these other effects. The same is true with like strategies of where to start exploration and so on. So we had to actually get a lot more robust and detailed about, we wanted to have a property that I could add a new experimental tactic or strategy to our fuzzer, and I would know that at worst it would only make things a little bit worse. But it turns out getting that property is quite hard.
Well, is a concrete example here, just so like people have some intuition for this. Like if we're testing a database, simulating like a complete failure of a hard drive is very likely to drive this system into a state which is like, it's not working, but it's not working in an uninteresting way that's totally expected, and no further fuzzing is going to make it interesting.
Right. That's not a bad example. Yeah. If you're maybe like the computer game example here is like if you have a tactic that like is always making you die and go back to the start of the game, like that is going to destructively interfere with other things that could be making progress.
The sort of natural thing that I would think to try, which you can tell me whether this works or whether it doesn't, is rather than bounding the total amount of energy, like bounding the total number of runs that a tactic can be used in. So essentially, like each run turn off some of the tactics so that a given tactic is turned on with only probability 1/n per run, say.
Yep, that's a good idea. That's basically swarm testing, which is a technique that we actually use quite a lot of. One of my favorite papers, by the way, and we talked before once about how it's also one of my favorite papers. Yeah, I guess for those who don't know, swarm testing is the idea that sometimes you can actually find more bugs in your system by turning off a subset of your tests. And if that sounds crazy to you, here is maybe a motivating example. And it's a good motivating example because it literally happened to me once. So imagine this like literally happened. You're designing a new cache data structure, right? And there's like two operations you can do on your cache. You can insert things and you can remove things, let's say. And so you go and you get Hypothesis, which is a great tool for testing data structures. And you're like, hey, I've got two generators. We can insert things, we can remove things. Go to town. And gosh, I'm brilliant. There's no bugs in my cache. This is so cool.
I see where this is going.
Right. The problem is the bug, which actually once caused an outage at Google, is in the garbage collection routine, which runs when the cache gets to a certain size. But I'm exponentially unlikely to generate a very, very large run of insertions without any intervening deletions from my cache, unless I was very clever about that and thought about that. And so what that means is that my test is actually not ever hitting this case. But if some percentage of the time when I'm testing, I just turn off the deletion method, then I will hit this very easily. And it turns out that insight generalizes to all kinds of testing of all kinds of stuff. It's really, really crazy how important this idea is and how not well known it is, given how important it is.
I was going to say, yeah, I'm also super fan of this paper. Earlier versions of Hypothesis actually implemented swarm testing by default. That feature got lost with a bunch of the changes to shrinking and serialization that happened in the 2.0 version of Hypothesis. Sorry, I think that was technically the 3.0 version of Hypothesis. There was a very short window between 2.0 and 3.0 because I screwed something up. And I've been meaning to put it back in for ages because it was a great feature. I think this is another case where also the trade-offs of like how much you're writing matter a lot, because I think it is a better feature for long-running fuzzers than it is for short-running fuzzers like Hypothesis.
Yeah, that's probably true.
This isn't a super well-validated theory on my part, but I think it's true. Certainly, I have never had an example where I've gone, oh, I should really add swarm testing back in so that this example doesn't happen. But I might not have noticed if I.
That makes a lot of sense. I mean, this is like I guess when I put my skeptical, busy industry programmer hat on, like this is a very interesting theoretical result. But like regular tests suffer from the same problem. Just like I wrote a lot of tests and they pass. I just didn't write a test to cover the important thing. And my sense is like we converge on solving that with test coverage. There's some like, red line along the side of your code in the pull request, and you got to make it bright red, which means that you've covered that chunk of code a bunch in the tests. But I rarely see things like this paired with property-based testing. Why not? Like, why isn't property-based testing more closely married with coverage guidance?
So in Hypothesis, there's a reasonable amount of work on combining with coverage, actually. Essentially none of it that I can take credit for. But you can plug a coverage-guided fuzzer in as the backend for Hypothesis. And there's...
But my recollection is you're not allowed to use it on commercial software.
That might be true. I think that is only for the hosted version. I think
okay.
I think that you can do it locally, but don't quote me on that.
Readers, you must read the license.
Yeah. As I say, I can take very little credit for the coverage guided fuzzing part. That was mostly Zach's work. I had always intended to add that as a feature, but never got around to it. So I was very happy when he did it for me. There's also, I'm afraid I'm blanking on the name, which is embarrassing. Taiki, I want to say, which is some quite a great work other people have done on visualizing what property-based testing is doing that is sort of coverage informed and does show you what lines are covered how often. So there's some work there. In terms of the general answer of why this is not as central a feature as it could be, I think a lot of it is this short test runtimes thing again. I think that most coverage-guided fuzzers, like there's a rule of thumb I have from a friend. I think this was actually Alex Gross who wrote the swarm testing paper, but I may be misremembering, that essentially American Fuzzy Lop starts being useful after its sort of first 100,000 or so examples. And because it's designed for fast tests and long-running fuzzing runs, that's fine. But if property-based testing is running only in your CI and as part of your development workflow, then you don't get to run 100,000 examples. You get to run 100 examples. And how to use coverage in a way that is useful in your first 100 examples is, I think, something of an unsolved problem.
I think that makes sense. I guess the thing that I was imagining was a little different, where, example-based testing, to its credit, right, is very explicit and very clear. And it's easy as a developer to have an intuition about the portions of your code that are being exercised by the example test you just wrote. But part of the point of property-based testing is to shove a lot of that into a somewhat more opaque black box where you're ceding control over exactly what's happening. And in the development loop, it feels like it would be nice to have some coverage guidance from some longer running process to inform me while I'm writing the test that I actually have not done a good job. And it would be nice to know that upfront instead of, 2 weeks later when I've gotten enough spare Borg cycles to find out that like actually there's 7 crashes that I would have found had I just thought a little harder or like let a coverage guided thing tell me that I missed some important chunks of code.
Yeah. I'm a big believer in 100% test coverage. Like I guess my personal feeling is that the point at which this should have been caught is like at the point of the pull request being opened and it showing you like here's the code in your pull request that hasn't been covered by the tests. I do often do like what is absolutely a poor man's version of what you're asking for, which is what at this point I add a bunch of assert false statements into my code where the code hasn't been covered, crank the number of examples that Hypothesis runs up to like 100,000 or so and run it and see where it crashes. And if it doesn't crashes, then something's gone wrong and I genuinely haven't covered that code. And if it does crash, great. I've now got some explicit examples to add to the source code.
Well, that's clever. That makes sense.
Now, this is a very janky workflow, and it would be much better if it did all this automatically for you. But at present, it doesn't do that.
Yeah, the antithesis answer to this is basically what we call sometimes assertions, which, formerly known as existential assertions. Basically an assertion that occasionally a given case is reached in the test campaign. And the nice thing about that is it's not just asserting that a location was reached, but potentially that the combination of a location and a condition was reached, which, I think my cynical answer to why most property-based testing people don't think a ton about test coverage is that it's because they're a little bit too perfectionist. And test coverage is a very, very lossy signal of how well your tests are covering your code. If you imagine trying to test a Python interpreter, if I achieve 100% coverage of that interpreter's lines, I have not begun to exercise that interpreter's behavior, and I think maybe this true fact is like a little bit too present in the minds of some PBT enthusiasts and means that we throw the baby out with the bathwater. But a sometimes assertion or an existential assertion does in fact let you get a little closer to that real MI testing.
That's another example, by the way, where the trade-offs between antithesis and hypothesis are very different. Like hypothesis very explicitly doesn't support existential or sometimes assertions because 100 test cases is not enough to reliably trigger them. And at that point, you've got flaky tests, and flaky tests are the end of the world. Like it's really important for anything property-based testing shaped to only stochastically fail like in cases where there's a real bug. And so it's obviously like you would like it to reliably fail, but if there are any bugs, but it's really important that it can only unreliably pass. It can't unreliably like a fail is not a false signal. And sometimes assertions on small numbers of test cases that you get to execute are just absolutely going to ruin that property.
Yep, that's super true.
Very briefly, sort of circling back to what we were talking about with LLMs and the sort of usefulness of property-based testing, and antithesis and hypothesis for them. I think that one of the big problems that we are with LLMs right now is that they are not very good at taking feedback. So I think even with this,
You're absolutely right.
Yes. Okay. Sometimes they're too good at taking feedback, but don't then incorporate it into their actions. So I think right now what you get when you incorporate these stronger signals into a vibe coding workflow or a standalone agent coding agent workflow is that you get an LLM that is essentially like repeatedly beating its head against the better tests. So one of the other things that I'm sort of interested in the moment, and I've been working with the sort of the GenLM group, who are a group of academics who work on sort of constraining LLM behavior, is to try and do things that sort of boost LLM reliability, and to sort of do more constraint generation and to sort of try and generally improve that end of the workflow. Because I think like right now, the way we're treating these LLMs is essentially like they're a magic oracle that can like you put in strings, you get out strings, and you don't have any other recourse to change their behavior than that, other than like changing the strings you put in. And I think that is very much going to sort of limit us and in terms of like making them a reliable component of software engineering. I very much don't have all the answers there, but I just sort of want to sort of note that like we need to sort of work on both parts of the puzzle. And like one part is how do you get them good enough feedback so that you can tell them when they're doing the wrong thing. But the other is like, how do you steer them to get them to do the right thing? And I'm sort of really hopeful that we'll be figuring that out over the next couple of years, because I think if we just try to improve like general purpose software engineering on one end and training on the other end, I think at some point we're going to get stuck, and it's going to be interesting to see when and where that happens.
Yeah, it is a little crazy if you think about it, that we have this incredible set of model weights, let's say. And the best, the first way that we figured out for extracting value from it was like slapping a chat interface on it and instructing it to like complete my sentence. And it worked really well for some things, and so then we've just like kind of gotten stuck with it. When there's probably like many other ways of like extracting value that like we haven't really thought about.
Yeah. Maybe not. Maybe this is a really deep thing where actually like software engineering as a discipline, like compared to many other fields of human endeavor, we have like really good objective functions for whether things are correct, or at least such objective functions are within our reach. And maybe the answer is that if the tool is only 80% reliable and we want one-shot answers without like repeated loops through the agent, that these are like fundamentally best suited for chatty interfaces where actually like the thing I want is a low effort answer where I don't care that much about its quality. Like I'm baking lemon cake, and like anything that vaguely resembles a lemon cake recipe is like kind of fine. I don't need like the French Culinary Institute version.
It's good.
I don't know. That's like it's a very dismal take on the utility of our current endeavors, but it seems hard to overlook.
Is it? So I was going to say it's probably true that we're never going to get the best possible version out of our LLMs, right? I think an LLM is in some sense a mediocrity engine, right? It'll give you a pretty good answer. It will never give you a great answer. And some of that, I think, is down to how we're training them. And some of that is probably just intrinsic. the reason I paused while saying that is I've actually had some very impressive conversations with ChatGPT about mathematics recently. It's not been producing world-shattering new mathematical results, but it has been behaving as a more competent human mathematician than I would have. It's not a human mathematician, but it's been behaving equivalent to a more competent human mathematician than I would have expected. So, but that's again a case where there's a really good objective function, right?
Is it also possible that the corpus of written mathematics is just definitionally produced by the 0.1% of best mathematicians? Versus the corpus of lemon cake recipes, which is polluted by people who have no idea what they're doing.
Or the corpus of software, which is
Look, we're not going to get there.
Yeah. No, it's true. But I think it has to be a feedback thing as well, because I think that if you were to try to ask ChatGPT a year, 2 years ago to do mathematics, even telling it to think through step by step in a way that is largely automated by think tokens these days, I think it would have produced garbage. And by the way, although I say it's been very impressive, this isn't to say it hasn't been making stupid errors as well. It's just that it's been producing quite high quality results, which sometimes contain errors, which I have to call it on. And oddly has been much better at taking corrections on its mathematics than it ever has been on its software. Don't know why that is.
I had kind of a similar experience, actually. I was recently trying to learn a new kind of math and a little bit of analytic number theory. And basically there was a thing I was having real trouble understanding, and I asked Claude to explain it to me. And its explanation, it wasn't perfect. It actually got a few things importantly wrong, which I was then able to call it on and be like, that doesn't make any sense, But it unstuck me, actually. It actually, it gave me a really useful analogy to think about, and it helped me relate it to something else I already knew. And I was like, wow, that was useful.
Mm-hmm. Yeah. I sadly have to report that ChatGPT is currently better at mathematics than Claude is.
You should try it.
At least in my experience. I've tried talking to both of them about mathematics, and I've found Claude at best unreliably helpful, whilst almost all of my mathematical experiences with ChatGPT have been good. I'm sure that this is by the time this podcast is live, even this may no longer be true. This is one of those things where everyone's leapfrogging everyone else all the time. But at the time of this recording, I much prefer ChatGPT for helping with mathematics than I do Claude.
Super interesting.
I think that kind of ties a neat bow on things, right? Even in this final little conversation, good objective functions and good reinforcement learning can turn imperfect tools into increasingly good partners for humans. And that can be true of LLMs as it is of tests.
Awesome. Thank you. Thank you so much for joining us, David.
Thank you very much for having me. It's been a pleasure.
Thanks for listening to the last episode of the Bug Bash podcast for 2025. We'll be back next year with new voices, topics, and more, all centered around software correctness and reliability. If you've enjoyed the show, tell your friends. And if you want to meet other like-minded people in person, consider attending the Bug Bash Conference, April 23rd and 24th in Washington, D.C. Find all the details at bugbash.antithesis.com. We'll see you next year.